Okay, good evening to everyone. I am Sakshi Bhardwaj and I am a PMRF TA under Professor Shishirchana in Chemical Engineering Department, IIT Roorkee, and I am currently a PhD scholar as well under Professor Pradeep Kumar Maji in Department of Polymer and Process Engineering, IIT Roorkee. And welcome to the session assignment 8 related questions of Polymer and Process Engineering. And this is the 8th session of this class. Before starting, let me introduce briefly myself. As I already told you, I'm Sakshi Bhardwaj. I'm in the Department of Polymer and Process Engineering, IIT Roorkee. The topic of my thesis is fabrication of cellulose-based aerosols for thermal management applications. Apart from it, I have completed my bachelor's from University of Delhi and master's from Maharishi Dayanand University. Also, I've conducted two projects, one in Indian Institute of Technology, Roorkee, over the lightweight thermal superinsulating aerosols, another one in the University of Delhi over repurposing of drugs for SARS-CoV-2. So, in the previous classes, we have read about different polymerization process, different polymers, the heat and mass transfer of polymers, and many properties related to polymers. Also, the processing conditions and how can we process the polymers. So now the basic and important topic about after the formation of polymers and polymers related products came the polymer testings. So how can we test the polymer whether it is up to the mark or not? So on the basis of that, we are starting our today's class. And here we are taking the questions related to polymer testing. So starting to what is the polymer testing? So polymer testing refers to any process to evaluate the physical, chemical, mechanical, thermal, and sometimes optical or electrical performance of polymers rather than polymers, plastics, rubbers, and composites itself to determine their quality, performance, and suitability for specific applications. So whatever applications we are targeting, we need to test how that polymer or the material behave in particular that. So in respective of that, we can test their physical properties, chemical properties, mechanical and other properties. So why these properties are required? So here are some key important points whether the testing requires. So first of all, these testing will ensure the material quality, confirm that polymer meets specific standards, either ISO, either ASTM. So these are the standards by which we can measure or test the polymeric samples. ISO is the Indian standard and ASTM is the American standard testing. And or other than the material quality, it is also important to detect defects or impurities or degradations in raw materials or the final products. And after the quality, it verifies the performance, like how a polymer will behave under real world condition, like heat, stress, and the chemical conditions, etc. It is help in predicting product lifespan and the reliability of the material. Next is the support product development. Aids in selecting the right polymer for a new applications, optimizes formulations, additive and processing methods. So it's important for like how we are developing a product and can this product be utilized in particular or targeted application. Fourth one is regulatory compliance. Required for certification in industries like medical, aerospace, automotive, or the food packaging. So it is also important like these, they meet the requirement standards for these. And that's why we need a certification that these materials can be used for automotives or the aerospace or the food packaging. That is why they can, how we can ensure the material safety and they are also environmentally compliant or not. Quality control is an important factor that comes under the polymer testing and that ensures in the production batches as well as the failures and returns or the repeatability of formation. Failure analysis like the reasons for product failure or the degradation like cracking, discolorations, and is important in the materials or designs. So that is how the polymer testings are required for the product formation and the use in the real-time applications. And based on these topics, we will going to do today's class and we are going to take some questions for today's class. Starting with the question first. So which of the following best describe accuracy in a measurement system? So they are asking about like which of the best describe the accuracy. How can we measure the accuracy? So first is the ability to detect small changes, the closeness of readings to the true value, repeatability of measurements or least count of the instrument. How can we describe that accuracy in a measurement system? It is a very easy question, I guess, because it is only the accuracy. Like we need to determine the values which is accurate. How can we determine the accurate? Either by the to detect the small changes happening in the system, either to closeness of readings to the true value, repeatability, or least count. All of the options seems to be correct for the accuracy, but there's one option which actually determine the accuracy in a measure system. Okay, I'm expecting some answers. You guys can answer like whether it's A, B, C, or D. Okay, let's move forward to answer then. Answer is B, which says its closeness of readings to the true value. And why is it? Because accuracy refers to how close a measured value is to the actual or a true value of a quantity being measured. For example, if a true length of an object is 10 centimeter, your instrument read should be 9.9 or 10.1. The measurement is considered accurate because it is very close to 10 centimeter, and that's how it measures that it is accurate or not. If the deviation from the accurate values the real time values is very much, then that means that is the accuracy is not there. And if you look at the other options like the ability to detect the small changes, yeah, this is important in measurement, but that doesn't describe the accuracy. Repeatability is important for the standard deviation and the mean, but not the accuracy. And the least count of instrument this describe the error, but for the accuracy, it describes by the closeness of reading to the true values. Like forever, whatever the true values are, if the readings are very close to them, it describes how accurate a measurement system is. It's a simple question, and like these, we will describe some more questions related to the measurement and the testing. Okay, then moving forward to the next question. Yeah. Which of the following is true about the t distributions? They're asking about the t distribution and which of the following statement is true. It is always narrower than the normal distribution. It is used only for categorical data. It is used when the sample standard deviation is unknown, or it is identical to the normal distribution for all sample sizes. So they are asking about which statement about the t distribution is true. Let us take 1 or 2 minutes and then we'll see if anybody answers. Otherwise, I will answer. Okay. Okay, let us see the answer then. So the line which is true about the t distribution is C, which says it is used when the sample standard deviation is unknown. So the t distribution curve is known generally when the standard deviation is unknown. And for that cases, we should know about what is the t distribution and how it does look like. So the t distribution is specifically designed for the situations where you're working with a small sample size. Where the working with a small sample size, especially commonly n less than 30, where and the population standard deviation in these cases is unknown. So they are asking if the readings of below n is equal to less than 30. So there we use these t distribution curves. Since we do not know such population standard deviation, we estimated is using the sample standard deviations. This introduces more variability and uncertainty, which is why we use the t distribution instead of standard normal distributions. If we look like at the curve of t distributions and other distributions, in the red, it is a t distribution in which n is close to 30, like or less than 30. If it is very smaller than 30, the t distribution look like very wide. So if we look at the first option, which says it is always narrower than this distribution, so it is wrong. No, it is always wide if you look at the curves. And if you look at the standard normal or normal distribution, so it is very narrower curve. So if you look at the other options, it is used for categorical data. It is and it is identical to normal distribution for all sample sizes. No, it is not identical to distribution for all sample sizes, and it is not used for categorical data also. So the t distribution curves look like this, and it is a part of statistical data. So we can measure these with which the very small sample size or the sample size with very small values less than 30. So these kind of distribution curves can be used in that case. And these curves are generally wider than the normal distribution curves. And where the smaller the t distribution, where the n value gets smaller to 30 and more smaller, the curves become wider in that case. So this is a part of statistics. Exactly. So they are some important topics in the polymer testing. We should know about these terms while testing the polymers, and that's how we can test the polymers in the different areas. So moving forward with the next question then. So which of the following is not a direct shaping method suitable for preparing standard mechanical test specimens? So they are asking about like if we need to measure the mechanical test, so how can we weigh the specimens, and which of the following testing technique cannot be used or shaping method cannot be used for shape the specimens? And options are extrusion, injection molding, compression molding, or the rotational molding. So which kind of these methods we cannot use to make the specimens? And if we look at the last session, which happened on the last Friday, we have read about what is extrusion, what is injection molding, what is compression molding, and the terms like that. So we exactly have an idea right now about these kind of processes and what kind of process, which kind of sample we can make from what these processes. So they are asking about when we cannot use among these techniques for the mechanical test specimens. And let's move forward to the answer. So which of the following is not a direct shaping method? So if we look at the options first, the first is the extrusion. So with the help of extrusion, we can draw a samples like the pipes, PVC pipes and hollow tubes and such as these samples. With the help of injection molding, we can form samples like with the specific mold. So these kind of techniques and the compression molding, like we can compress and mold a sample. So these kind of techniques we can use for make test specimens for the mechanical testing. Only if we look at the rotational molding. So it's a different term, rotational molding. These kind of molding process will not be used and cannot be used for forming the test specimens. And that's why the not direct shaping method is D, which is rotational molding. Let us look at what is rotational molding. So rotational molding, or we can also call the roto molding. It is used for large hollow plastic parts such as tanks, containers, playground equipments. And in this case, the powder plastic is placed inside a hollow mold, which is heated and rotated so that the plastic melts and coats the inside walls. And such as these kind of, if you look at this instrument, so this is a powder which we can put in the mold, and that it is a circular mold like this. And on the heating and rotating this kind of mold, when it is rotating like this, the polymer will take the shape of this mold. Polymer will take the shape of this mold, and such kind of specimens can be formed by this type of rotational molding. And these kind of specimens, which we generally do not use for mechanical testings. And if we look at the characteristics, not precise in terms of dimensional accuracy, first of all, it can produce thick walled hollow parts. So it is not suitable for making standardized test specimens, which require tight dimensional control and solid geometry. So if in this case, because we need to test, so such as mechanical testing, so we need a proper specifications of sample. Anything deviated from the proper specification, which we cannot use for mechanical testing, because mechanical testing and other testings are based on ISO and ASTM standards, and these standards have required shape and dimensions for all of the samples. And if those techniques cannot make the such as the same samples every time, so these type of techniques cannot be used for this mechanical or the other testing specimens formation. So rotational molding is one of those which we cannot use for the formation of test specimens. Rather, we can use extrusion, injection molding, and compression molding techniques to make this. I hope the rotational molding concept is clear and the question is also very clear to all. If yes, we can move forward to the next question. Okay. So this question asks which process is commonly used for producing complex high precision test specimens with tight dimensional tolerances. So in the last question, it has asked about like which of the following technique we cannot use for the test specimen formation. And in this question, it is particularly asking like which of the following technique: blow molding, injection molding, rotational molding, or extrusion. So among these techniques, which of the following technique have the high precision test specimens with the tight dimensional tolerances or tight dimensional, I can say, specifications? So what technique we can use to form these kind of specimens among those? Okay, we can just suggest that rotational molding is out of the concept right now, because in the last slide we have seen that this technique cannot be used. But rest other techniques, they can be used for formation of such specimens. But if we talk about the precision, which technique is highly precise? Okay, let's move forward to the answer. So among these, the method which can use or the technique which can use to form high precision test specimens is the injection molding. And if we look at other like blow molding and extrusion, these are also the processes, but with the molds itself, the highly precise mold is of injection molding, in which we can inject the polymer, melted polymer, and form the specific shape. If we talk about the extrusion, it is a continuation process in which the formation of polymer is like continuous, and for that we need to cut the sample according to that specific size, so it's not that precise. And if we talk about the blow molding, so such kind of techniques used to form the hollow plastic bottles or such things. And that's why if we talk about the high precision test specimens, so these the technique which can be used for these are injection molding techniques. And if you look at the injection molding, the purpose of injection molding is to produce complex, detailed, and high precision plastic parts. And the process contains molten plastic injected under high pressure into mold cavity and then cooled and solidified. And that's how the specimen is formed. And we also discussed this technique in the last session. So if you want to read about more in injection molding or the other processes like blow molding and extrusion, you can guys can refer to the last. And the advantages of injection molding is first, they have the excellent dimensional accuracy. Second, it has the smooth surface finish, repeatable because it can be great to make multiple identical specimens because the mold size is fixed every time. And complex shapes are possible like thin walls, detailed features. So it can be used to form different complex shapes. And it is also used widely standard mechanical test specimens like ASTM or ISO test bars. So this is the technique which we used for the forming of test specimens. I hope this is very clear topic. It's very clear, the easy one too. Okay, let's move forward to the next question of this class is a low fill factor in the mold cavity may lead to. So they are asking about like a low fill factor in the mold cavity may lead to overpacking, flesh formation on the part, incomplete part formation, and warpage due to high pressure. So if it or mold cavity have the low fill factor, what could be possibility then among all these options? Okay. Let us repeat the question and then move forward to the answer. So it is asking about a low fill factor in the mold cavity, which can lead to overpacking, flash formation, incomplete part formation, or warpage due to high pressure. So if we look at the question itself, so they are asking about the mold cavity. And if we look at the cavity, so if we talk about the processes, so we just read about the injection molding and other processes, the blow moldings which require the cavities to form. So if a low fill factor, so what happen is the correct answer is C, which says it's incomplete part formation. Because if the fill factor is low and if it is cannot be filled completely, so the part formation will be incomplete. And if you look at the overpacking of mold, no, this will not be the case for low fill factor. Flesh formation of the part. Flesh formation we have read is the extra part present after the filling of cavity. Whatever extra remains, it came out of the mold and which we can term as flesh. And D, which is warpage due to high pressure. So no, this is also not the case. So for the low fill factor, if you look at the answer, the fill factor in the injection molding refers to percentages of mold cavity that is filled with molten material during the injection phase. So if it is a high fill factor, that means the cavity is nearly or fully filled, or the extra which came out, which form the flash. So it's the flash formation on the part in the high fill factor. For the case of low fill factor, it means the cavity is not adequately filled, which leave the empty or the partially filled regions, and that is because the reason or the outcome is incomplete part formation in that case when empty or the void present in the cavity. And if the polymer cannot fill all the cavity, that means the part will be formed incompletely, and that's the low fill factor which can cause the incomplete part formation in the case of injection molding. I hope this question is clear. They are very basic questions based on testings as well as the processes we have already studied in the last session. So they are not that tough, but while moving forward, we will introduce some more concepts and some more techniques to test polymers, which will be helpful for the polymer testings. Okay, then move forward to the next question. So which of the following best describe a short defect in injection molding? So they are asking about a short defect in injection molding. So in this case, the mold is overfilled, the cavity is only partially filled, the molten plastic degrade during injection, or the mold cycles is too fast. So how this defect which says short define as? Okay, then move forward to the answer. So, which of the following best describe a short defect? And the answer is B, which says the cavity is only partially filled due to low fill factor. In the last question, we have read about the low fill factor, and they are asking about the short effect. So, if we look at the short effect, that the name itself suggests that the short, like the unfilled part of it. And if we look at this, so molten plastic does not completely fill the mold cavity in this effect, which led to an incomplete or malformed part. This usually results in missing sections or poor surface finish. And why this happens? First is the low fill factor. Another one is insufficient inject pressure, or the speed is insufficient to fill or the inject in the mold cavity. Last is the poor flowability of molten plastic or blockage. So they says that either the poor flowability of molten plastic, like the molten plastic has a higher viscosity, because viscosity also plays an important role. So if it is not completely molten and it is already in the stage of like a viscous, so this happens due to this. And last is blockage or poor mold design. If injection, which is injecting into the mold, if it has some blockage in it, which also can resist the cavity to completely fill, and that's how this defect can also be possible. So there's these factors which we can take into the mind after before forming the material. And this is a defect which says it's short defect. Okay, then this is clear. So let's move forward to the next question. Okay, so it's a question which says which device measures the flow behavior of polymer melts under pressure and is typically used in quality control for thermoplastics. So they are asking about which device can use for flow behavior of polymers. So options are melt flow indexer, flow cup, wicket apparatus, or durometer. So among all these four options, which device can measure the flow behavior of polymer melts under pressure and generally can be used for quality control of thermoplastics? Okay, then if let's move forward to the answers. So the device which measures the flow behavior of polymers is first the melt flow indexer, and how the melt flow indexer works and how it can measure the flow behavior of polymers. So if you look at the machine, which is look like the melt flow indexer, and it is also known as the melt flow rate tester. It's a laboratory instrument which we can use for measure how easily a thermoplastic polymer flow when melted under a standardized pressure and temperature. It determines the melt flow index, like what is the mass of polymers which flow through a small die in 10 minutes under a specific load and temperature. So here, if we can pour the uh, polymer material or the plastic material, so under the temperature and the pressure condition, it melted and then flow through this cavity, and how much or how many grams of polymers can flow through this cavity in 10 minutes. That's how one can measure the melt flow index. And if you look at the apparatus, so this is the piston which can move the polymer. Example, this barrels can heat, and they are the test specimen like the polymers, and that's how from there here the polymer will flow, and how much it flow we can collect this into the speaker and then can measure the weight after 10 minutes. So what is the weight of this polymer which we can use to calculate the melt flow index, and that is very important property for the injection moldings and other processing for these kind of thermoplastics. So that's how a melt flow indexer works and can use for quality control of thermoplastics generally. And why it says only thermoplastics and not thermosettings? Because the formation or the melting of thermosettings is very difficult, and that's how the thermoplastics can always melt and can be used in melt flow index and also can recycle. And that's how why thermosetting plastics, because they once set cannot be melted that easily and that cannot be recycled. So this is also only for thermoplastics or thermoplastics based materials. Okay, let's move forward to the next question then. So it is asking which property of material is the most directly determined using an extensiometer during a tensile test. So it is a question on tensile testing. So it's asking about which property of a material is most directly determined using an extensiometer during a tensile strength. So the tensile strength measure the toughness, the ductility, the tensile strength, or the Young's modulus. What does this extensiometer measure? Okay, moving forward to the answer. So the most directly determined material property measured by accentometer is D, which says it's Young's modulus. I guess, yeah. So the extensiometer is a precision instrument. Extensiometer is a precision instrument which is used to measure the change in length of a material when it is subjected to a load, especially in tensile testing. It generally capture the elongation of a specimen over the defined gauge length during loading. So they generally measure the elongation and the change in length of a material. So to read more about these tensile testings, I have prepared a specifically slide for this. So if you look at this, the stress strain curve. So the stress strain curve of the tensile testing of a polymer generally look like this, in which first it will go like that, this, and then after the yield strength, it will go like this, and then the fracture. And if we look about the reasons, so the first reason states that it is an elastic reason. In this case, material can return to its original shape after the load is removed. So this is the elastic region of any material, that how the material show elasticity during this. And whenever this yield point is reached, there is the point which the permanent plastic deformations begin. So here the elasticity will diminish at this point, and that's how the plastic deformation starts. And now this further reason is the plastic reason. Mainly material deform permanently and cannot return back when we remove the stress from it. And that's the ultimate tensile strength, this point where there's the most tensile ultimate, like the most peak of the curve, which says is the maximum tensile strength a material can reach. After it, this strength material will got fracture at this point. And this is the necking and the fracture. Necking tells the material get thinner during this, and then it fractures at this point. That's how this curve can define, in which the Young's modulus, which we can measure with the help of the formula which says stress upon strain. So it's a property that defines its stiffness, or we can say from elastic to plastic deformation. So it is the slope of the stress strain curve. So here you can measure this point by the slope. So this perpendicular upon base, this says the stress, this says the strain. So it's a formula of directly define the ratio of stress upon strain. Stress is calculated by force measured by tensile machine, and strain is measured using the extensiometer. So that's how the strain can be measured. So to calculate Young modulus, we have the actual strain data, which is exactly what extensiometer provides. And that's how this extensiometer can help in calculating the Young's modulus rather than other factors like hardening, ductility, toughness, and all these things. And that's how this curve looks like of the tensile, which we generally known as the stress strain curve for the tensile testing. And it's mainly described the 3 to 4 things, like first is the elastic deformation, and then yield point. After yield point is the plastic deformation, where the strain hardening or the hardening of a polymers happen, and then at a point it start necking, like the thinning of the polymers, and the final point is the fracture, and where the ultimate tensile strength comes. And the Young's modulus, which also helps us to determine the property of a polymer, which we can calculate from the stress strain. So that's how this curves look like, and this is the mainly the important points of this curve. I hope this curve is clear to everyone. And if yes, we have some questions related to this curve. So starting with the questions. So they are asking about the main objective of tensile strength. So what is the main objective? Why we need to measure the tensile strength? And because it is to evaluate a polymer's what? Optical properties, the electrical resistance, behavior when stretched or pulled, and resistance to solvent. So what kind of property we can measure from the tensile testing? Okay. So yeah, the answer is C, which says it's measure the behavior when stretched or pulled in the tensile testing. Yes, because if we look at the other properties like the optical properties, so no, the tensile testing is cannot be used for the optical property measurement. So it cannot be used for the optical property measurement. It cannot be used for the electrical resistance. It cannot be used for the resistance to solvent. The only property which it can be used to measure is when stretch or pull, like how the material behave when stretch or pull. So if you look at the curve, the real time curve for the stress strain, which looks like this. This is the elastic deformation, yield point, then plastic deformation has the ultimate tensile strength, then the necking start till the fracture point. And that's how the specimen will look like. Like first of all, the specimen will look like this. It's a dope cone, or we can say, yeah, it's dope cone sample. And if we start pulling it around, so it from this point it will start thinning, and then it will look like this, or more force, it will look like this. And finally, it says necking, like the thinning from this point, and finally it will get fractured. So up to this point, this material will behave elastic, like on the removal of stress. Also, it will gain again its shape. And then after the instant, this will start getting permanently deformed, like plastically, and cannot be returned to its shape. So that's how this area will look like. And that on the ultimate tensile strength, after this, the necking will start and it will get thinning at this point, and finally it got fractured. So that's how the tensile test is performed. And generally, if we look at the tensile test and the definition, so it's a fundamental mechanical test where a sample is subjected to a control, tension, or pulling force until it deforms or breaks. So tensile testing directly assesses the mechanical behavior of a polymer under the tensile load. It helps determining important properties such as tensile strength, elongation, how much the sample can be elongated before breaking, and the Young modulus, which can say measure stiffness or the resistance to elastic deformation. And these properties are very critical for understanding like how the polymer will perform in applications involving pulling or stretching forces. Like if we need to pull a material, so how it will behave like this. So this generally measure the property, and that's how the tensile testing works. I hope this concept is clear to everyone. So let's move forward to the next question. And this is a question of measuring the Young's modulus. So it's a numerical based question which says a wire which is a 2 meter long and with a cross sectional area of 1 millimeter square is stretched by a force of 100 Newton. And if the extension is 1 millimeter, what's the Young's modulus of the material? And below the options. So we just read about the Young's modulus formula, and we can just simply put the formula to calculate the Young's modulus. Okay, so I'm just writing the formula here. So this Young's modulus, we can just denote by Y or by E itself. If it can be calculated with the stress on strain. And if you look at the question, so we are not provided anything by stress or strain. So we need also to calculate the stress and the strain. So if you look at the stress, so stress generally defined by the force by area. So force per unit area, which says it's the stress, and the strain, which we can calculate with the length or the extension. So it's can define a change in length of a material with the original length. So that's how we can calculate the Young's modulus by these formulas. So if we look at what we are provided with, so we are provided with original length of a wire, which says it's 2. So the L value will be 2 in that case. And then the cross-sectional area, which says is 1 millimeter square. So the area is like 1 millimeter square. And the force which is provided is 100 Newton. So the force can be 100 Newton. And the extension, like the change in length, which is 1 millimeter. So the 1 millimeter of this value. And that's how we can put all these values and calculate how many what is the value of Young's modulus. So if we look at the answer, which says it's B, which is 10 raised to power 11 Pascal, and which we calculate with the help of this formula. This is a modified formula of this, like with the help of the stress, we can denote by force per unit area, and the strain, which we can denote from delta L by L. So that's how we can simply put the values of F, which says is 100, the L, the original length, which says is 2 meter long, and that's the area of which says it's 1 millimeter square, and the delta L, which says it's 1 millimeter. So that's how I guess this the value of this 2, this 2 is extra here. So this is not the case. So if we look at the option, this 2 is not. So B is not. The correct option will be C. Says is 2 into 10 raised to power 11 Pascal. So if we solve this value, so we will get the value of 2, because this 2, I don't know where it came from. I just by mistakenly write that. So it's the 2. It's 2 into 10 raised to power 11 Pascal in this case. But yeah, that's how the concept defines. Like if we need to calculate the Young's modulus, we can simply calculate the Young's modulus with the formula of stress upon strain. And if we do not provide it with the stress or the strain, and if any of these the value is asked, we can calculate by this formula. Like sometimes it can be asked like what is the force acting, and the value of Young's modulus is given, and it's sometimes asked what is the extension, what could be the area. So we can calculate these kind of variables from this formula itself. So I hope this concept is clear that how can we calculate the Young's modulus in this case. Okay, let's move forward to the next question. So how does strain rate affect the tensile property of a semi-crystalline polymer? So they're asking about like how the tensile properties of a semi-crystalline affected by the strain rate. Either that can be increased, increasing strain rate generally decrease the tensile strength. Increasing strain rate has no effect on tensile behavior. Increasing strain rate usually increases tensile strength and stiffness, or strain rate only affect optical properties, not mechanical. I hope by looking at the formula, the options, we can simply eliminate the D1 because the strain rate affects mechanical, not the optical. So it's not possible. So only 3 options will remain, A, B, and C. So what is the formula for the semicrystalline polymers? How the strain rate affects its tensile properties? Okay, let's move forward to the answers. So the stress strain affect the tensile properties of a semicrystalline polymers by increasing strain rate. It generally increases the tensile strength and stiffness. So at high strain rate, the polymer chains have less time to rearrange or relax. That's how the material responds more elastically and resists deformation. This results in increase in tensile strength and stiffness because the polymer behave more rigidly and resists the applied load more effectively. So they're saying that when the polymer do not have time to rearrange, so that's how that it will show the more elasticity, and that's how the tensile strength of this material can be increased, which increases the stiffness too. So it because of the high strain rate, that's how the semicrystalline polymer will behave. Okay, I hope the concept of tensile strength is clear and how we can calculate the tensile strength and the Young's modulus and the different properties in the strain curve is clear to all. Yes, yes, and let's move forward to the next question, or we can say the next concept. So here we have already read something about rheology in the previous sessions, and there we are going to take some questions because rheology or rheometer is also an important testing in the case of polymers. So the question is, what does an extensional rheometer measure? They are asking like, what is an extensional rheometer measure? Viscosity under shear, change in color, resistance to elongational flow, or surface roughness. So what does an extensional rheometer measure? Okay, so the extensional rheometer measures C, which is phase resistance to elongational flow. So what is extensional rheometer and how it looks like? So this is an extensional rheometer and it is a specialized instrument used to study how materials behave when they are stretched or elongated rather than sheared. It measures the material resistance to deformation under tensile, pulling, stretching forces, which is known as extensional viscosity or elongational viscosity. So that's how elongation extensional rheometer works. This is a specialized instrument like this. If you can see, it has two special drums, and the sample is holded like this, and it can stretch the samples, and that's how it can measure the elongation rather than shear. It measures to used to measure material resistance to deformation until the tensile force, which is known as extensional viscosity or elongational viscosity. So it is actually measure the resistance to elongational flow. So how it can be elongation, how the it can the show the flow, that how this rheometer measures. There are different type of rheometers. So this how the extensional rheometer works. Okay, then if the extensional rheometer is clear, so we will move forward to the next one, which says the rotational rheometer. So how the rotational rheometers are best suited for measuring which type of material behavior. So what is the rotational rheometer measure? Tensile failure, elastic and viscous behavior, electrical conductivity, and creep rupture in materials. So among these, what property can be measured by rotational rheometers? Okay, so rotational rheometers measure the elastic and viscous behavior under shear. And that's how the rotational rheometers look like. And the rotational rheometer are generally designed to apply rotational shear deformation on a material or measure how it responds. So if we look at them, we can put the sample here, and this it can rotate either the top plate or either the cone. So it can rotate actually the cone or the plate. So that's how the shear deformation is measured due this rotational rheometers, and the mainly used to study the shear viscosity, like how the material flow under the shear stress, the elastic behavior, like the material stores energy like a spring, the viscous behavior, like the how material dissipate energy like a fluid. So this is important to measure the viscoelastic materials such as G double dash are recorded, like the storage modulus and the loss modulus measured during these elasticity, like how much energy it can store and how can be stored as to show the elasticity, and the dissipated energy in the form of loss modulus can be measured with these kind of rotational rheometers. Generally, materials like polymers, gels, paste, emulsion, food products, paints, and coatings, which we can use in rotational rheometers for the dynamic testing, and the small oscillating strain is applied and the material storage modulus and the loss modulus are recorded. So these kind of materials which can be used to measure the elastic and the viscous behavior of those under the shear stress after the rotation. So there are two we have just read about the in the previous slide, which is the extensional rheometer, which says the elongation, which measures, and here in this case it measures the shear viscosity and the elastic or the viscous behavior of polymers or the other materials like gels, paste, emulsions, and foods. Okay, so after the reading of rheometers also, here is also one question which on the rheology, which is the shear thinning behavior observed in many polymer melts means. So they are asking that the shear thinning behavior, which is observed in many polymers, what does that mean? Either the viscosity increase with increased shear rate, viscosity decrease with increase in shear rate. Shear rate has no effect on the viscosity of polymer degrade under shear. So we have read shear thinning behavior in the rheology classes, and there's the question from that class we can relate. Like we have read already what is shear thinning. So how does polymers? Why this polymers shows the shear thinning? And how the shear thinning means what? Either viscosity increases, decreases, no effect, or the polymer degrade under shear. What does that mean? Okay, so shear thinning, if we recall our last classes, so shear thinnings increase, the viscosity decrease with increases the shear rate. So this is the behavior of a polymer, which is the polymer melt consistence of long entanglement of molecular chains. At the low shear rates, these chains are randomly coiled and entangled, causing higher resistance to flow, so viscosity is generally high. When the shear rate increases, the chains begin to align and stretch in the flow direction. These alignment reduce entanglement and internal resistance, making the melt flow very easily and the viscosity decreases. So if we look at the example of ketchup and honey, so generally they have high viscosity and cannot be dumped. But when we squeeze them out of the bottle, so that's where the shear rate, when we increase the shear rate, so the chains of those polymers or those things align, and that's how the viscosity decreases and it came out very easily. So these are some examples of to show the shear thinning behavior, and that's how the polymer also reacts. So after applying the shear stress or the shear rate, when increased shear rate is applied, the chains align, and that's how the viscosity of those polymers can decreases and they can flow. So that's the option B is correct, like viscosity decrease with increasing shear rate. I hope this concept of measuring the rheology and different properties why the with the rheometer is clear to everyone. Yes, if yes, we can move forward with the next question. So this is a question which says what property is directly evaluated by a polymer hardness test. So they're asking about the polymer hardness test and what kind of property we can measure from the polymer hardness test. Flexural impact resistance to surface deformation or the melting temperature. So what property is directly evaluated by a polymer hardness test? And if we look at the properties, so it's the correct answer for the polymer hardness test is C, which says the polymer hardness test is used to measure the resistance to surface deformation. And if you look at the word itself, it says the hardness. And if we got the hardness, so it's the resistance to surface deformation, like how hard a polymer is. And the rest of the properties like flexural strength. So flexural strength is used to measure the bending of polymer. So in this case, it is concerned from the bending. Impact is like how much the polymer can withstand the sudden shock from any we can say the material. So it is the impact, like how impact it will. And the melting temperatures, the melting temperatures are different. We can measure the melting temperature with the help of BSC. At what temperature it melts. So this is not any concern to polymer hardness test. So only the option which remains is the resistance to surface deformation. And if you look at the hardness testing measure methods, so hardness measure a material resistance to localized surface, such as indentation, stretching, and abrasion. It reflects how well a polymer surface can withstand mechanical damage from contact with other material. Like we need to put some material over the polymer, so how much it can withstand. So that's the material hardness. And if we look at the measurement, so we can just this type of pointer, we can measure the hardness. So such kind of pointer we can place on the polymer surface. So it is like the minor primary load, whatever it has on it, and then we can apply load above it. So that's how the measure load, and that's the total load can calculate it, like the minor primary load and the measure load. And this is the minor after removing this, the minor primary load remains. And if you look at this, so the displacement after the load, this H we can use to calculate the hardness. So that's how, like after applying the stress, how much it the surface is deformed. That's how we can measure the hardness of any polymer. Okay, then moving forward to the next question. Oh, that's the last question. Sorry. And with these, we can say that we have read some of the testing techniques like the tensile, the rheology, the hardness, and the basic testing parameters which we need to keep in mind while testing the polymers. And we can also say that the polymer testing techniques we will also take in the next session as well, because it's a 2-week class of polymer testing. So with these questions, you guys can easily solve the week 8 assignment 8. So I wish you all the best for week 8 assignment 8. I hope this class is clear to everyone. And yeah, thank you to all. We'll see you in the next session.